Welcome back to the Deep Dive.
Always a pleasure.
Today we'll be taking a look at probability,
Ah, yes, the science of chance.
or to quote the American philosopher, C.S. Peirce.
A formidable mind.
Probability is simply the science of logic, quantitatively treated.
A succinct definition.
And that quote really captures the essence of our deep dive today,
Indeed, we'll be exploring the logic of uncertainty
using the elegant tools of mathematics.
to unravel the mysteries of chance.
Now we've got some dense material in front of us today.
A veritable treasure trove of probability concepts.
But our mission
Should we choose to accept it?
is to distill these complex ideas
Into a clear and intuitive understanding.
for you, our listeners.
No matter your background in mathematics,
We'll be focusing on the fundamental building blocks of probability.
the essential toolkit for grappling with chance.
So we'll be covering conditional probability,
The probability of an event given that another event has occurred.
Bayes' theorem,
A powerful tool for updating our beliefs,
the idea of independent events,
where the occurrence of one event doesn't affect the other.
and finally, the binomial distribution.
A cornerstone of probability for repeated trials.
So buckle up
And get ready for a wild ride.
through the fascinating world of probability.
It's going to be an insightful journey.
So let's jump right into it with conditional probability.
Sounds good to me.
This concept is all about how the knowledge that one thing has happened changes the likelihood of something else happening.
It's about the interplay of events and how they influence each other.
Our source material kicks things off with a classic example.
One that's sure to get those mental gears turning.
Imagine tossing 3 fair coins.
And we're talking standard coins, heads and tails.
What are all the possible outcomes?
Well, we can list them systematically.
Let's see, you could get all heads,
Right, HH.
2 heads and a tail,
HHT.
or head, tail head,
HTH.
or tail head head.
PH.
You get the idea.
All the possible combinations.
Now, assuming these coins are fair,
Each outcome is equally likely.
so each has a 1 in 8 chance of occurring.
A probability of 1/8.
Now let's narrow our focus to 2 specific events.
This is where conditional probability starts to shine.
Let's call the first event E.
And define event E as getting at least 2 heads.
So that includes HHH, HHT, HTH, and THH,
4 outcomes in total.
meaning the probability of E happening is 4 out of 8.
Or simplified, 1/2.
Now for our second event.
Let's call this one F.
And event F is defined as the first coin shows a tail.
So this includes the outcomes THH, THT, TTH, and TTT,
Again, 4 outcomes.
with a probability of 1/2 as well.
Now here's where it gets really interesting.
The heart of conditional probability.
Imagine we know for a fact that event F has occurred.
We're told that the first coin landed on tails.
How does this new information
This crucial piece of knowledge,
change the probability of E
the
happening?
probability of getting at least 2 heads.
It's like the game has changed,
Our perspective has shifted.
and we have to reevaluate our understanding of the possibility.
Exactly. We can no longer consider all 8 outcomes.
Because we know the first coin is a tail.
So we eliminate those outcomes where the first coin was heads.
Our universe of possibility shrinks.
It contracts down to just the outcomes in event, F.
THH, THT, TTH, and TTT.
Our sample space is reduced.
Now, within this smaller set of outcomes,
This new reality we're working with,
how many of them also satisfy event E?
how many have at least 2 heads?
Well, just one.
Only THH fits the bill.
So out of our 4 possible outcomes,
Only one meets both conditions.
meaning the probability of E happening, given that F has already occurred,
This is what we call conditional probability.
is 1 out of 4.
Or 1/4.
See how that initial piece of information
But the first coin was tails.
completely changed the probability?
It reshaped our understanding of what's likely.
Conditional probability is all about this interplay.
How one event influences the likelihood of another.
Now let's formalize this concept with a definition.
The mathematical framework behind conditional probability.
We write the conditional probability of E given F as P of E given F.
Using that vertical bar to symbolize given.
And it's defined as the probability of both E and F happening together,
The intersection of those events.
divided by the probability of F happening.
Provided, of course, that the probability of F is not 0.
You can't divide by 0.
That's a mathematical no-no.
So let's go back to our coin toss example.
And connect this definition to our intuitive understanding.
The event where both E and F occur
Getting at least 2 heads, and the first being a tail,
is just the single outcome, THH.
with a probability of 1/8.
And we know the probability of F
The first coin being a tail.
is 1/2.
So if we plug these values into our formula,
P of E given F equals P of E and F divided by P of F,
we get 1/8 divided by 1/2.
which simplifies to 1/4.
Exactly as we reasoned before.
The formula aligns perfectly with our intuition.
It's a precise way to express our understanding of the situation.
Now, there are some handy properties of conditional probability
Useful relationships to keep in mind.
that make working with these concepts a bit easier.
Let's take a look. First off, think about the probability of the entire sample space S happening.
Given that F has already occurred,
In other words, if F has happened, what's the probability that something happened?
well, since the sample space S includes all possible outcomes,
It's a certainty.
so P of S given F equals 1,
Similarly, if F has already happened,
that's the probability that F happened.
again, it's a sure thing.
So P of F given F also equals 1.
It's like saying, if it's raining, what's the probability that it's raining?
Or if you're holding a red ball, what's the probability that you're holding a red ball?
It's a 100% guarantee.
Another useful property involves the union of two events, A and B.
The probability that either A or B or both happen given that F has occurred.
This is equal to the probability of A given F plus the probability of B given F.
And then we subtract the probability of both A and B happening given F.
That last part accounts for any overlap between A and B.
To avoid counting the same outcomes twice.
Now, if A and B are mutually exclusive,
Meaning they can't happen at the same time.
then that last term becomes 0.
And the formula simplifies to just the sum of the individual conditional probabilities.
What about the probability that E doesn't happen given F has happened?
That's a good one. We call this the complement of E.
Written as E with a little apostrophe.
So P of E prime given F is simply 1 minus P of E given F.
It's the opposite of E happening.
So in our coin example, the probability of not getting at least 2 heights
Knowing the first coin was a tail,
would be 1 minus 1/4,
which equals 3/4.
a straightforward calculation.
These properties are really helpful.
They give us shortcuts and alternative ways to approach problems.
Now let's solidify our understanding with some more examples.
Practice makes perfect.
Our source material provides a nice variety.
So we can see how conditioning probability applies in different scenarios.
Let's start with a simple one.
To warm up our probability muscles.
Say we know the probability of event A is 7/13.
Okay, so P of A equals 7/13.
And the probability of event B is 9/13.
So P of B equals 9/13.
And the probability of both A and B happening together is 4/13.
That's P of A and B, the intersection, equals 4/13.
Now the question is,
The challenge we face.
what's the probability of A happening?
What's the likelihood of A?
Given that B has already happened,
We're given that B is a certainty.
how does that affect the probability of A?
That's what we need to figure out.
Well, we have our trusty formula,
P of A given B equals P of A and B divided by P of B.
so we just plug in our known values,
Substituting what we know.
4/13 divided by 9/13,
And those 13s cancel out nicely.
leaving us with a probability of 4/9.
Simple and elegant.
Conditional probability in action.
It's all about how information shapes our understanding of probability.
Now for a classic puzzle.
A brain teaser that often trips people up.
A family has 2 children,
We don't know the order they were born in.
but we know at least one of them is a boy.
Given this information,
What is the probability that both children are boys?
it's tempting to say 50%.
Because, well, there are 2 possibilities.
Either the other child is a boy or a girl.
But conditional probability tells us to think a bit deeper.
It's not that simple.
Let's break it down.
Analyze it carefully.
Our sample space
All the possible combinations.
could be boy, boy,
BB,
girl, boy,
GB,
boy, girl,
BG,
or girl, girl,
GG.
assuming each combination is equally likely.
Each has a 1/4 probability.
Now, let event E be both children are boys.
So E is just the outcome, BB.
And let event F be at least one child is a boy.
So F includes the outcomes, BB, GB, and BG.
Now, the event where both E and F occur
The intersection of E and F.
is just BB.
Both are boys, and at least one is a boy.
So P of E and F is 1/4.
And the probability of F, at least one is a boy.
Is 3/4. And
So the conditional probability of E given F,
P of E given F is 1/4 divided by 3/4.
which simplifies to 1/3.
Not 1/2 as our initial intuition might have suggested.
This is where conditional probability really challenges our thinking.
It forces us to consider the specific conditions.
And adjust our probabilities accordingly.
Let's try another scenario.
Another chance to practice.
Imagine 10 cards numbered 1 to 10.
Okay, I'm visualizing them.
You randomly select one card.
Pick one at random.
Now, if you know the card is greater than 3,
So we're given this information.
what's the probability that it's also an even number?
Another conditional probability puzzle.
Let's define our events.
Our sets of outcomes.
A is the event the number is even,
So A is the set 2, 4, 6, 8, 10.
and B is the event the number is greater than 3.
So B is the set 4, 5, 6, 7, 8, 9, 10,
The intersection of A and B
where both conditions are met.
is the set 4, 6, 8, 10.
The even number is greater than 3,
So the probability of A and B is 4 out of 10.
and the probability of B is 7 out of 10.
Therefore, P of A given B
The probability of the number being even given, it's greater than 3,
is 4/10 divided by 7/10.
which simplifies to 4/7.
See how the knowledge that the card is greater than 3
That constraint we were given.
affected the probability of it being even.
It narrowed down the possibilities.
Okay, one more conditional probability example.
To really get a good grasp on this concept,
And this one's a bit more involved.
a multi-stage scenario.
You toss a coin.
A standard heads or tails coin.
If it lands heads,
Okay, one possibility.
you toss the coin again.
A second toss.
But if it lands tails,
The other possibility.
you roll a standard 6-sided die.
Okay, two different paths depending on the first toss.
Now the question is,
The probability challenge.
what's the probability that the die shows a number greater than 4,
That's our target outcome.
given that at least one tail occurred in the experiment?
So we know at least one tail happened, but we don't know which path we took.
So we need to consider all the possibilities.
And their associated probabilities.
Their sample space consists of pairs.
Reflecting the outcomes of both stages.
So we can get heads, tails,
T-tails.
tails 1, tails 2,
T2.
and so on up to tail 6.
T6.
Now, each of these outcomes has a specific probability.
Assuming a fair coin and a fair die,
The probability of HH is 1/4.
because we need heads on both tosses.
The probability of HT is also 1/4.
Same reasoning.
And for each of the tails number outcomes,
Like T1, T2, and so
the
on.
probability is 1/12.
Because the first toss needs to be tails, which has a probability of 1/2.
And then any specific number on the die has a probability of 1/6. So 1/2 times 1/6 equals 1/12.
Now let's define our events,
Event F is at least one tail occurred.
which includes HT and all the tails number outcomes.
The probability of F is then,
Let's see, 1/4 plus 6 times 1/12,
which is 1/4 plus 1/2.
or 3/4.
And event E is the die shows a number greater than 4,
That's just T5 and T6.
and the intersection of E and F
The outcomes that satisfy both conditions.
is also just T5 and T6,
So P of E and F is 1/12 plus 1/12.
or 1/6.
Now we can finally calculate P of E given F.
1/6 divided by 3/4,
Simplifying that gives us 1/6 times 4/3,
or 4/18.
which reduces to 2/9.
See how that initial condition of getting at least one tail
That knowledge we were given.
drastically changed the probability of getting a number greater than 4 on the die.
It highlights how important it is to consider the context.
Conditional probability is all about that.
Now that we have a solid grasp of conditional probability,
Let's move on to a closely related concept,
one that builds on what we've just learned.
the multiplication theorem of probability.
This theorem provides us with a powerful tool.
For calculating the probability of 2 or more events happening together,
It's especially useful when dealing with sequences of events.
where the outcome of one event can influence the next.
The multiplication theorem is a direct consequence of our definition of conditional probability.
Remember, P of E given F equals P of E and F divided by P of F.
Well, if we rearrange that equation,
A little algebraic manipulation.
right, we get P of E and F equals P of F times P of E given F.
And similarly, we can express it as P of E and F equals P of E times P of F given E.
It's just a matter of perspective.
So if we want to know the probability of both E and F happening,
The probability of their intersection,
we can take the probability of one event happening
either E or F,
and multiply it by the conditional probability of the other event happening.
given that the first event has already occurred.
It's a straightforward way to calculate the probability of a joint event.
Our source material gives a good example to illustrate this theorem.
A classic probability problem involving drawing balls from an urn.
An urn, you say? Sounds intriguing.
Imagine an urn filled with 10 black balls and 5 white balls.
Okay, I can picture it.
You randomly draw 2 balls from the urn.
One after the other.
But here's the catch.
The twist.
You don't put the first ball back in before drawing the second.
So the first draw changes the composition of the urn for the second draw.
Exactly. We're drawing without replacement.
which means the events are not independent.
The outcome of the first draw affects the probabilities for the second.
Now the question is,
What's the probability that both balls you draw are black?
so we're looking for the probability of a sequence of events.
2 black balls in a row.
Let's define our events.
E is the event that the first ball drawn is black.
And F is the event that the second ball drawn is black.
Now, the probability of E
Drawing a black ball on the first draw,
is 10 out of 15.
because there are 10 black balls and a total of 15.
Now, we've already drawn 1 black ball.
And we haven't replaced it.
For the second draw, there are only 9 black balls left.
And a total of 14 balls.
So the probability of F given E
Drawing a second black ball given the first was black.
is 9 out of 14.
Now we can apply the multiplication rule.
To find the probability of both E and F happening,
P of E and F equals P of E times P of F given E.
so that's 10/15 times 9/14,
Multiplying those fractions gives us 90 over 210.
which simplifies to 3/7.
So the probability of drawing 2 black balls in a row without replacement is 3/7.
And the multiplication theorem made this calculation quite straightforward.
It provided us with a clear path to the solution.
Now, what if we have more than just 2 events happening in sequence?
Can we extend this rule?
Absolutely. The multiplication rule generalizes quite naturally.
For any number of events.
For example, if we have 3 events,
Let's call them E, F, and G.
the probability of all 3 occurring together
P of E and F and G.
is equal to P of E times P of F given E times P of G given both E and F.
So we're essentially multiplying by the conditional probability of each event.
Given that all the preceding events have already occurred,
It's a chain of conditional probabilities.
our source provides a good example to illustrate this.
A card game scenario.
Imagine drawing 3 cards without replacement from a standard deck of 52 cards.
Okay, I'm picturing the deck and the draw.
What's the probability of drawing a king, then another king, and then an ace?
In that specific order,
We need all 3 cards to meet their conditions.
let's represent these events as K1, K2, and A.
K1 for the first king, K2 for the second king, and A for the ace.
We want to find the probability of K1 and K2 and A.
The probability of the first card being a king is 4 out of 52.
Because there are 4 kings in a standard deck.
If the first card is indeed a king,
And we don't replace it.
there are only 3 kings left.
And 51 cards remaining.
So P of K2 given K1 is 3 over 51.
And if we've already drawn 2 kings
There are still 4 aces left.
out of 50 cards,
So P of A given both K1 and K2 is 4 over 50.
now we can apply the extended multiplication rule,
To find P of K1 and K2 and A,
multiplying our conditional probabilities together,
we get 4 over 52 times 3 over 51 times 4 over 50.
which equals 48 over 132,600.
Simplifying that fraction gives us 2 over 5,525.
So the probability of drawing a king, then another king, then an ace without replacement is quite small.
But the multiplication theorem gave us a systematic way to calculate it.
It breaks down complex sequences into manageable steps,
This theorem is really useful
a versatile tool in our probability toolkit.
for analyzing scenarios where events happen in stages.
And the outcome of one stage can influence the next.
Now let's shift our focus to a different concept,
A fundamental notion in probability.
the idea of independent events.
This is where things get a bit simpler.
Independence means that whether one event happens or not,
It has absolutely no impact on whether another event happens.
they are completely unrelated in terms of probability.
It's like flipping a coin twice.
Getting heads on the first flip doesn't change the probability of getting heads on the second flip.
Those events are independent.
Now let's define this more formally.
To ensure we're on the same page,
2 events, E and F, are considered independent.
we say E and F are independent.
If the conditional probability of F happening given that E has happened
So P of F given E.
is simply the same as the probability of F happening on its own.
So P of F given E equals P of F.
In other words,
To put it another way,
knowing that E has occurred.
it doesn't give us any new information about the likelihood of F.
And the same applies in the reverse direction.
The conditional probability of E given F equals the probability of E.
So P of E given F equals P of E.
They don't influence each other.
Now here's a really important consequence of independence.
A key property to remember.
If E and F are independent,
If they satisfy those conditions we just discussed,
then the probability of both E and F happening together
P of E and F, the intersection.
is simply the product of their individual probabilities.
So P of E and F equals P of E times P of F.
This multiplicative property is often used as the working definition of independence.
Because it captures the essence of the concept.
Now, it's crucial to distinguish between independent events.
And another type of event we've encountered.
Mutually exclusive events.
These are very different concepts.
Mutually exclusive events cannot occur at the same time.
They have no overlap.
Their intersection is empty.
And the probability of their intersection is 0.
Independent events, on the other hand,
Can have common outcomes.
their occurrences just don't influence each other's probabilities,
If they coexist peacefully,
like flipping a coin and rolling a die.
those are independent events.
The outcome of one has no bearing on the other.
But they can both happen simultaneously.
You could get heads and a 3.
It's perfectly possible.
Now, when we talk about 3 or more events being mutually independent,
Extending the concept of independence to multiple events,
say A, B, and C,
it's not enough for them to just be independent in pairs.
pairwise independence doesn't guarantee mutual independence.
We need a few more conditions to hold.
For mutual independence, we require that the probability of A and B happening together
So P of A and B.
must equal the product of their individual probabilities.
P of A times P of B.
And similarly for A and C and for B and C.
So P of A and C equals P of A times P of C.
And P of B and C equals P of B times P of C.
All the pairwise intersections must satisfy the multiplicative property.
And crucially, the probability of all 3 events happening together
P of A and B and C.
must also equal the product of their individual probabilities.
So P of A and B and C equals P of A times P of B times P of C.
This ensures that the occurrence of any combination of these events.
Doesn't influence the probabilities of the others?
It's a higher level of independence.
Mutual independence is more restrictive than pairwise independence.
Let's look at some examples from our source material.
To solidify our understanding of these concepts,
Imagine rolling a single 6-sided die.
a standard fair die.
Let event E be the number rolled as a multiple of 3,
So that's 3 or 6.
and event F be the number rolled as even.
So that's 2, 4, or 6.
Are E and F independent events?
To answer that, we need to check if their probabilities satisfy the conditions for independence.
The probability of E, P of E, is 2 out of 6,
Because there are 2 favorable outcomes out of 6 total possibilities.
which simplifies to 1/3,
And the probability of F, P of F, is 3 out of 6.
or 1/2.
Now the intersection of E and F
The event where the number is both multiple of 3 and even.
is just the outcome 6.
So P of E and F is 1/6.
Now we check if P of E and F equals P of E times P of F.
Does 1/6 equal 1/3 times 1/2?
Yes, it does.
So in this case, E and F are indeed independent.
Their occurrences don't affect each other.
Here's another example involving rolling a die.
But this time we're rolling it twice.
Okay, 2 rolls,
Let event A be getting an odd number on the first roll.
and event B be getting an odd number on the second roll.
Are A and B independent?
Intuitively, they should be.
Because one roll shouldn't influence the next.
But let's confirm this mathematically,
The probability of getting an odd number on a single roll
whether it's the first or the second.
is 3 out of 6 or 1/2.
So P of A equals P of B equals 1/2,
Now, the event A and B,
getting an odd number on both rolls.
since the rolls are independent,
The probability of this is simply P of A times P of B.
which is 1/2 times 1/2 or 1/4.
We could also list out all the possible outcomes.
To verify this,
There are 9 outcomes where both rolls are odd,
out of a total of 36 possible outcomes.
again giving us a probability of 1/4,
So A and B are indeed independent.
as we expected.
Our intuition aligns with the math.
Now let's look at an example with 3 events.
To see how things can get a bit more nuanced,
You toss 3 fair coins.
3 tosses, heads or tails.
Let event E be the outcomes, H, 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 and T, T, T.
So all heads or all tails.
Event F be at least 2 heads.
So HHH, HHT, HTH, and TH.
And event G be at most 2 heads.
All the outcomes except HHH.
Now the question is,
Which pairs of these events are independent?
to answer that we need to calculate probabilities and check for independence.
P of E is 2 out of 8, or 1/4.
P of F is 4 out of 8, or 1/2.
And P of G is 7 out of 8.
Now for the intersections.
E and F have only one outcome in common.
H, H, H.
And 1/8 does equal 1/4 times 1/2.
So E and F are independent.
But what about E and G?
Their intersection is just T, T, T.
So P of E and G is 1/8.
But 1/4 times 7/8 is 7/32.
which is not equal to 1/8.
So E and G are dependent.
The occurrence of one affects the probability of the other.
And finally, F and G.
Their intersection is HHT, HTH, and THH.
So P of F and G is 3/8,
But 1/2 times 7/8 is 7/16.
which is not equal to 3/8. So F and G are also dependent.
This example shows that pairwise independence doesn't guarantee mutual independence,
It's possible for pairs of events to be independent.
but not for all three events to be mutually independent.
It's an important distinction to keep in mind.
Our source material also mentions a useful theorem about independent events.
A handy shortcut.
If two events, E and F, are independent,
Then E and the complement of F
written as F with a little apostrophe, F prime,
are also independent,
and so are E prime and F.
and E prime and F prime.
So the relationship of independence extends to their opposites.
If knowing about E doesn't tell you anything about F,
Then it also won't tell you anything about F not happening.
and vice versa.
This theorem can save us a lot of calculations.
And finally, for two independent events, A and B,
Another handy result
the probability that at least one of them occurs.
is equal to 1 minus the probability that neither of them occurs.
So that's 1 minus P of A prime times P of B prime,
Sometimes it's easier to calculate the probability of what you don't want.
and subtract it from 1.
It's a useful trick.
Now brace yourselves.
Because we're about to delve into one of the most powerful and often surprising concepts in probability.
Bayes' theorem.
A concept shrouded in a bit of mystery.
But once we understand it,
It unlocks a whole new way of thinking about probability.
Bayes' theorem deals with what's sometimes called reverse probability,
It can feel like we're trying to predict the past.
like using current knowledge to figure out what might have happened before,
But at its core, Bayes' theorem is about updating our beliefs.
or our probabilities.
In light of new evidence.
It allows us to calculate the probability of